Osterberg. Erich Osterberg is a climate scientist for Dartmouth. I believe he's in the Earth and Geological Sciences area. Is that correct, Erich?
Yeah, we call ourselves Earth Sciences.
Earth Sciences, yeah. So about at least half the screen that you're looking at is also involved in the Earth Sciences. So there's a heavy abundance of Earth science and geologists here, and so they're right in your camp. Erich has been to Denali, he's been to Greenland, he's been to Antarctica all numerous times. You're going to get to know him a little bit better tonight in the Science Cafe. We have a couple films that kind of detail some of his exploits. But today, he's here to talk to you about, I'm going to turn it over to you, Erich.
So can you see my screen as a presentation view?
Not yet.
Yes. Yes. Because
Okay.
Oh,
you might have to escape again, Bill.
All right, perfect. Well, welcome everybody. Good to see you all virtually. I feel like I know you a little bit. I've been checking out the Padlet, which is kind of fun for me because with the whole COVID home learning, I have two kids, a 7-year-old and a 10-year-old. So my 10-year-old was in 4th grade and they had a Padlet page set up for their 4th grade class. So that became part of I'd never heard of it before the pandemic, but that's how his 4th grade class was keeping in touch. So I'm familiar with Padlet now. And yeah, so I feel like I got to know you guys a little bit by seeing some of your posts from yesterday evening. So what I want to talk about for the next 30 minutes and then make sure we leave time for questions is just introduce you to ice core records in general, like what do we learn from ice cores, talk a little bit about Greenland and Antarctic ice sheets, and then we'll talk about ice age cycles and what ice cores can tell us about ice age cycles. And so to begin, I'll just pose this question: like, what do we actually need ice core records for? What are they good for? And I think probably the most pressing reason is because if we want to understand something about the climate, how the climate fundamentally works, we need records of that. And obviously, the best records we have are things like from weather stations with thermometers and barometers and wind meters and everything else. But that record is at most, about 150 years long, reliably, more than just a few records that go back further. But the best record we have is really just 100 years long, and this is that surface temperature record I'm showing here, which clearly shows global warming as we come to know it. This goes all the way up to 2019, our most recent data. So that far point on the right, you can see is the 2019 data point, which was the second warmest year record behind 2016. And so far this year is shaping up to be another top 5 year. So we need these ice cores to be able to extend this back, not just 100 years, but to go back 1,000 years or 10,000 years or a couple 100,000 years in order to understand how the climate system fundamentally works. The other thing that is really helpful about getting records in the past is that we can use those records of the past to make sure that our climate models are working well. And so when we look in the past, we call this making hindcasts. When we look in the future, of course, we call those forecasts. So what we do is that we use our climate models. So these are the global scale models that we use to try and predict future temperature, the kind of plots that I'm showing below, where you could imagine either business as usual, where we keep emitting a lot of CO2 and other greenhouse gases, and we see somewhere around 8 degrees of warming, or that's Fahrenheit, by the way, 8 degrees Fahrenheit warming by the end of the century. Or if we really reduce our CO2 emissions, then you're looking at something like half of that, 4 degrees of warming. But in order to make sure that this model is actually telling us a realistic projection of the future, what we could do is figure out what the past looked like and see if the models can reproduce that in their hindcasts. And if they can, then that gives us some confidence that they're doing a reasonably good job of projecting into the future. So a lot of the ice cores that we collect, we collect from the 2 ice sheets, Greenland and Antarctica. Not all of them. Pretty much any glacier on the planet is fair game for ice cores, and we've gone to quite a few of them. But a lot of the research focuses in Greenland and Antarctica. So let's talk about those 2 ice sheets. So here's a map of Greenland showing on the left here some of the key ice core locations that have been drilled going back to 1966, when the very first deep ice core that was drilled anywhere on the planet was collected up at Camp Century, which is up here in the northwest part of Greenland near Thule Air Force Base. So that was a kind of an interesting core because that was, there were actually Dartmouth undergraduate students there to help drill that core. So for me as a professor at Dartmouth, it's really cool to be continuing on this tradition of ice core research when we were there from the beginning. It was actually researchers just up the road here at the Army Research Facility that were in charge of that drilling operation. To then fast forward to the early 90s, there were these two ice core records in the middle of Greenland called GISP-2 and GRIP. GISP-2 was a US expedition and GRIP was a European one. And these are still some of like the most critical records of past climate that we have, because they proved the existence of really rapid climate change. And here I'm talking, you know, something on the order of 15 degrees Fahrenheit or more in the span of just a century or so. So huge changes, and Bess Kaufman will actually be talking about this in like an hour and a half from now. So stay tuned for more on rapid climate change from her later. I'm not going to really talk about that here. And then, you know, pretty much every ice core gives us some new insight about the climate or about pollution. I'll talk a little bit about both. And the other thing that we think about, do you guys see, or is that just me?
I see a mouse moving.
Okay, but you don't see the buttons in the way. So, okay, good. So, you know, one of the key things that we worry about in the future is sea level rise. And so if we worry about Greenland melting, it's important to know that about 23 feet of sea level equivalent is stored in the ice sheet in Greenland. So if you were to melt all of Greenland, sea level around the world would go up by about 23 feet. And we're going to come back to that idea in a couple of minutes.
Get on. Why?
So if we think about what an ice sheet looks like in terms of cross section, if you were to slice it in half, this is what it would look like. So essentially you have an area near the top that we call the accumulation zone, and this is where snowfall accumulates and doesn't melt the next summer. So maybe some of it melts, but not all of the snow will melt the next summer. And then it'll go down and it'll eventually flow out to the edges where we call the ablation zone. And that's where more ice melts every year than actually it flows into that spot. So you have net gain of mass in the accumulation zone and net loss of mass in the ablation zone on the edges. And so each ice sheet is you can think of it as a conveyor belt of ice. It's starting up at the top and then it's flowing out to the edges where it eventually melts. And this takes hundreds of thousands of years if it's a big ice sheet. If it's a small glacier, it might just take a few decades. But what's really neat about the big ice sheets is that they store a lot of time in the ice. It's also interesting to think about what's underneath this ice, right? So it's not always the same in underneath every glacier. Underneath Greenland's ice sheet, if you were to strip it all away, what you'd actually find is a large island that has it has mountain ranges, it has canyons. It's a really complex topography. It's not just sort of, you know, flat. It's as complex as any other topography out there. It's just that it's been covered by 2 miles of ice. One interesting difference though between Greenland and Antarctica is that almost all of this ice is based above sea level, so that if you were to remove the ice sheet, that would all be land above sea level today. The Greenland island would be above sea level. But we'll see it's a little different down in Antarctica. So let's flip to Antarctica. And there's been a lot of ice cores collected down in Antarctica as well. These are some of the big projects, and these are not just US projects. These are by all sorts of international groups, including European groups, Asian groups, and American groups. And it doesn't really matter too much about each of these, but you'll hear a little bit about the Vostok ice core later on in a video that I show, and you might recognize some of these other names from some of your readings or activities. And so some highlights from the Antarctic ice cores versus the Greenland. What's really neat about Antarctica is that the ice is so old there. So in Greenland, we can only go back about 110,000 years in time. In Antarctica, we've already gone back 800,000 years, so about 8 times longer. And we think that we can go back 1,000,000 years or more. Some people think maybe 2 or 3 million year old ice is present there in Antarctica somewhere. So that's a difference with Greenland. It's much older ice. And then the other difference is that we can measure CO2 in the ice cores in Antarctica much better than we can in Greenland. And that's because Greenland has too much chalk dust in the ice itself. So calcium carbonate dust, chalk, that is deposited on the ice, that actually interferes with our CO2 measurements. Whereas Antarctica has much lower levels of that. And so we're able to measure the amount of CO2 in the ice really precisely. So all of our best records of CO2 come from Antarctica. And once again, there's just so many papers. I mean, thousands of papers that come out about these cores, each with a really interesting insight about climate or pollution through time. And then if we were to melt these two ice sheets, so of course there's 2 ice sheets in Antarctica, the West Antarctic and the East Antarctic. The West Antarctic ice sheet is about 16 feet of sea level equivalent, and East Antarctica is a whopping 190 feet of sea level equivalent. So East Antarctica is massive. And remember that Greenland was about 23 feet, so just a little bit bigger than West Antarctica. And then if we strip away the glacier on top of Antarctica, the 2 ice sheets, this is what we find. So everything in yellow and red here would be above sea level, but everything in blue and blue here, and actually green as well, would be below sea level. And so what that means is that on the left-hand side of this figure, in what we call West Antarctica, this is really a group of islands that have been covered by an ice sheet. Okay, it's different from in Greenland, where it's just this one big island, almost like a small continent. Here, most of the West Antarctic ice sheet is actually based on what we would consider to be like underwater sediments, marine sediments. And that means what we think is that West Antarctica is much less stable than, say, East Antarctica is, which is kind of like Greenland. It would be high and dry if the ice sheet wasn't there. So East Antarctica or Greenland, both of which are above sea level. West Antarctica is below. And so that means we think that it's a lot more susceptible to melting quickly. Okay, so what can we learn from ice cores? Just really quickly, and then we'll talk about this in some more detail. You know, temperature, we can get a lot of information about temperature, CO2 or greenhouse gases, how much snow falls every year. We can get records of how stormy it is, and we can see how changes in pollution have occurred over time. And that's what's really critical about these records, is that they don't just give us a snapshot. They give us a continuous record over time of how these things have changed. And usually, we're not just getting one record from the core. We're usually getting all of these records from the same core. And that's really powerful, because if you can get the same record from the same core, you can get temperature and you can get CO2, then you can really know what the relationship between temperature and CO2 is. You don't have to worry about any artificial mismatch between 2 different cores. You can get the same different information from the same core. All right, so you folks just did that really cool penny exercise, which I've done with Bill and Louise. And so I'm not going to go into detail here about 18O and 16O. You guys are well familiar now that 16O is our easier to evaporate, that lighter isotope, and our 18O is preferentially condenses out, our heavier isotope. And so that if you start near the equator, then you measure the isotopic ratio, the relative weight of the 16O and 18O in snow and rainfall, that it's pretty close to 0, which is shown in red here, near the equator. And as you get closer to the poles, it gets lighter and lighter and lighter and lighter, as there's preferentially more and more of that lighter 16O isotope. So what this shows us is that we can use the stable isotopes to infer changes in temperature through time in an ice core. And so that's what I'm showing here is in the top plot, I'm showing changes in that ratio of 18O and 16O in an ice core. And the point here is that you can see each and every single year. And that's because, of course, in the summertime, things are warmer, and so we get a little bit more of that heavier 18O isotope. And in the winter, when it's colder, we get less of that 18O isotope. And so we can see these annual cycles in the isotopes. And that means that we can actually count back each individual layer in the ice core, just like we can count layers in a tree, like looking at tree rings. And it turns out that it's not just isotopes that we can do this for. I'm also showing you in red a magnesium record at the bottom, which stands for the amount of dust in the ice core. So this ice core record happens to come from Alaska. And in Alaska, dust gets blown in from the Chinese deserts every spring. And so that creates a big spike in dust pretty consistently every spring. And so just like the isotopes have that consistent seasonality, in this case, so does the dust. And in putting both of those records together, we can have a lot of confidence that we're seeing these annual layers through time in the ice core. And that's really powerful because if you go back in time, you can note each individual year when something happened. Most proxy records that we use, say a core from the ocean or from a lake or something like that, they have some uncertainty in just how old each part of the core is. But often with ice cores, we can get extremely precise into knowledge about just how far back in time it is. So once you do that, you can actually see the thickness of each record and figure out how much snow fell in each year going back through time. In this picture, what I'm showing is you can actually see it in what we call a backlit snow pit here, okay, where each couplet of light and dark represents 1 year, where the dark snow represents the denser summer snow, and the light layers represent the lighter winter snow. And so you can see there's a layer right here, and then another layer here, another layer here, another layer here, and then at the top here would be one large layer. So you can see it in the density, you can see it in the isotopes, you can see it in the dust. There are all sorts of different ways that we can pick out these annual layers. And so I'll just show an example of what this might look like. This is a record from one of my grad students, Dom Winsky. This was a record of snowfall through time in Alaska from an ice core from Denali. And so on the left side of the plot is 1,200 years ago, so 800 CE. And then on the right side of the plot is today. And so what's being plotted here is snowfall, or annual accumulation, the amount of snow that fell each year. And it's in meters of water equivalent. And so I've turned that into snow, just to give you a sense. So back here, before the industrial age, we used to get on average about 8 feet of snow every year on top of this mountain. And now we get more like 18 feet of snow every year. And so again, we were able to figure this out by looking at these annual layers that we can see in the snow and figuring out just how thick they are. Another way of getting temperature, so isotopes are one good way, but another way of getting temperature is by actually looking at what we call melt layers in the ice core. So this is, what these represent is times when the temperature was just a little bit above freezing at that exact location. Maybe just for a couple days or just a couple of hours in a particularly warm afternoon. And so the surface of the glacier will melt, and that melt water will trickle down into the snow and then refreeze. And so that's what you're looking at here. You're actually looking at an ice core placed on its side and sliced in half. And then we have light coming up from beneath it. And so these dark layers here represent normal snow that has been crushed into the ice core. So snow that has not been affected by melt. But then these light bands are these refrozen melt layers. And this represents an individual afternoon when it warmed above freezing. And so what we can do is we can measure the thickness of these. We can see how frequent they are going down through the core, which is of course going back through time. And we can turn that into a record of melt through time, which relates to temperature. And so we did this in Greenland a couple years ago. A team that I was leading, we started down at the southern part of this map where the star is at die 2. And then at each red dot here, we collected an ice core. And it took us about 2 months to get all the way up to summit. And then the next year we went back to summit, and then we took another 2 months to get this northern loop and collect another 9 ice cores. And the idea was we were trying to figure out how Greenland had melted going back in time, how the temperature had changed and how that had changed melt. And so this just gives you a sense of what our camps look like. So we are totally, fully out there. in full expedition mode, totally self-sufficient. We were on snowmobiles. There's about 5 of us in each team. And so these little tents are the tents that we would sleep in. You can see there's just 4 of them because one person slept in this little emergency pod. He didn't want to set up his tent every day. And then these larger tents are our kitchen tent and our research tents where we keep our computers and our charging equipment and such. And then you can see where we're drilling the ice core over here. And so this is what a typical expedition in Greenland might look like, a small expedition with just 5 people. And then this is what our record looked like. So here I'm actually plotting the amount of melt through time. You know, how thick are these melt layers going through time? Going back to about 1550 CE, so about 450 years ago. And then on the right side is today. And so what we were able to show is that the amount of melting that we're seeing today, which is really just since the mid-1990s, is when this gets above past levels of melt. That these levels of melt we're seeing today are truly unprecedented for at least the last 450 years. And evidence that we have from other places suggests that it's probably since at least 8,000 years ago that we've had temperatures this warm. So in addition to temperature, we can also, and snowfall amount, we can also tell things about like storminess. So pretty much anything that falls out of the atmosphere gets recorded in the ice core. So that means that anything that's up in the atmosphere eventually falls out. So that includes things like sea salt and big storms that blow over the ocean, like this nor'easter I'm showing here. They pick up sea salt from the ocean and it gets blown around in the atmosphere and it'll eventually settle down on top of the glacier. And you can imagine that when the winds are stronger, meaning when the storms are stronger or there are more storms than normal, that you would end up with more sea salt getting blown up on the glacier. And that is actually what we see. You can do the same thing with dust. You can imagine that if the winds over the desert regions are stronger, we're going to get more dust blown into the atmosphere and then deposited on the ice sheet. And I don't know if you folks have been paying attention to the news lately, or if any of you are right now down in the southeast part of the country, but we've got a huge dust storm right now, right? This is a dust storm that blew from the Sahara Desert, and it's made its way all the way across the Atlantic, all the way over the Caribbean, and now it's up into southeastern United States. Beautiful sunsets, but a real health hazard, actually. The concentrations are high enough. They're saying that this is the largest Saharan dust storm in 50 years. And so the question is, well, what's going on climatologically to make that happen? And the answer is that the winds over the Sahara Desert are much stronger right now than they normally are. So you can imagine that if there was a glacier here, it would be recording that higher amount of dust. It would show up as a huge spike in dust. And we'd be able to say, whoa, something really weird happened in 2020. It appears that the winds coming from the Sahara Desert were really stronger than normal. And in fact, that is what's been happening. And then, of course, pollution. So again, anything that's up there in the atmosphere, it can eventually rain down, and we can record that in the glacier. So whether it's greenhouse gases or things like acid rain, so sulfate and nitrate, we can show how these have changed through time in the ice core. And now, of course, you can go out there now and actually sample how much acid is in the atmosphere right now. But what's really interesting about the ice cores is that they allow you to go back in time and see what it used to be like before human activities. It gives you that baseline of what natural conditions used to be like, because none of us have been around long enough to know what that was actually like, and we don't have scientific measurements of how much acid or CO2 was in the atmosphere at that time. We need ice cores to tell us that. And so when you look at that, it's really quite dramatic, right? CO2 was very flat until the Industrial Revolution. Same with methane, same with sulfur and nitrogen, which are acid rain. They've all got this hockey stick shape to them. And without the ice cores, we might just know what was happening for the past couple of decades, but we wouldn't have this natural context to understand what was really happening. I think one of the most important records that we have from ice cores is from greenhouse gases. So unlike everything else I've been talking about, which we call a proxy for past changes, meaning it's not an actual measurement of, say, temperature, but it's actually a representation of temperature, like the isotopes. here we actually have what you can imagine as like tiny little jars from the ancient atmosphere, preserved as bubbles in the ice core. So this is not actually a proxy. What we actually do here is we melt the ice core, and we can actually measure the amount of CO2 that was in the ice core back in time. And that tells us what the CO2 was in the atmosphere. So these pictures are showing you some of these tiny little bubbles in the ice core where the CO2 is trapped. So not a proxy. And so this is sort of the classic record of temperature as determined by the stable isotopes in red, and CO2, which is shown in blue above it. And in this case, you got to be careful here, but time is going from left to right. So 800,000 years ago is on the left, and today is all the way on the right. And what we can see is in temperature, we can see there's a lot of changes up and down and up and down and up and down. And each one of these downs is actually another ice age. And each ice age was associated with really low CO2. Okay, so I think a lot of students think about the ice age, right? There was one ice age. But what the ice core records show conclusively is that there were lots of ice ages, regularly spaced going back in time. And the one that we think about, the ice age, is just the most recent one that ended about 20,000 years ago, when temperatures were cold and CO2 was low. One of the interesting things to also look at is what happens when you're in between these ice ages like we are today. So here's today, we're in between ice ages, but here's the last time, 125,000 years ago. And if we look at that, what we see is that sea level was actually 16 to 26 feet higher 125,000 years ago than it is today. And at that time, temperatures were about 2 to 4 degrees warmer than today. And so this is what Florida looked like at that time. And this is not based on, models or something like that. This is based on the fact that if you go to these areas of the Florida Peninsula, it is actually covered in limestone that we know formed underwater. Okay, these rocks formed underwater. So by combining this kind of evidence of where sea level was with this kind of evidence of how climate changes, we can get an understanding of where we're headed in the future as we continue to warm. So this is what this causes is quite a bit of uncertainty in sea level estimates going into the future. So what I'm showing here are different sea level curves going all the way out to 2100. And the red is if we put a lot of CO2 in the atmosphere, and the blues are if we put a lot less CO2 in the atmosphere. But you can see that there's this huge uncertainty on the top part of the high CO2 estimates. And that's because we know that this is what happened the last time we were 2 to 4 degrees warmer. We know that. What we don't know is how quickly that happened. And so if it happened really quickly, or if the ice sheets can melt really quickly, then we're going to be at the higher end of these uncertainties. If it turns out that it takes, say, 1,000 years for the ice sheets to melt that much, then we'd be closer to the lower ends of these. But we actually don't know. So there's a lot of uncertainty there in sea level. The other thing that, of course, this shows is it shows us what the natural range of CO2 was going back for almost 1 million years, right? Naturally, the lowest that we ever see CO2 in blue here is around 180 parts per million. And the highest that we ever see it over the last 1 million years might be this point here, which is just shy of 300, around 290 parts per million. So that's the natural range of CO2. And of course, today we're at 415. That's actually yesterday's number, 415.6. Okay? So if we put that on this curve, here's what the ice cores tell us the natural range is, and then here we are here. And here are where we're headed, either under a low emission scenario or a business as usual scenario, where by the end of this century, we hit somewhere around 900 parts per million, 3 times the highest CO2 that we can see in the ice core record going back 1 million years. And remember that our species showed up on this planet somewhere here between 200 and 300,000 years ago. Okay, so our species, Homo sapiens sapiens, have never seen CO2 of this magnitude. We also know that the rate of speed at which the CO2 is rising today is truly unprecedented. So the fastest natural rise in CO2 that we can see, like these look like they're pretty fast, but the fastest that those are is 0.015 parts per million per year, versus today we're rising at 2.1 part per million per year. So 140 times faster than natural. So not only are we off the chart in terms of where we are, right, 415 versus the max should be 300, but it's rising 140 times faster than we see naturally. The last time CO2 was this high was at least 3 million years ago. Estimates are uncertain because the ice cores don't go that far back. The ice cores are the best way we know CO2. There are some other ways that we can infer it, but they have big uncertainties. And so it may have been as long as 15 million years ago. And then as we keep going up by 2.5 ppm every year, that the time since we've last seen that keeps going further and further backwards. So I think I'm going to stop it there because we're at 30 minutes and I want to leave time for questions. So please, any questions that you folks have, happy to answer.
What did you give for your estimate of the modern human, date-wise?
Oh, in terms of evolution showing up?
Yeah.
Yeah, so somewhere between 250, 300,000.
Okay.
Erich, this is Rose. I have a question regarding taking the ice core. So I have two questions actually.
Yeah.
So when you guys are taking the ice core, how much impact this experimentation or taking samples would have on the area? Like how do you guys determine where to take the ice core and like if it has any impacts? And the second question would be, based on the results from Arctic and Antarctica, are they yielding similar results? Like when you think about the last, let's say 800,000 years, oh, maybe you didn't have the ice core from that long from Arctic, but whatever the timeline, are they actually resulting in similar, outcomes?
Great question. So
I have one question.
Yeah.
If I can say that now, what is the source of the limestone chalk for the Arctic region, for Greenland?
Great question too. So I'll try and hit all three of these, okay?
Thank you.
The first one about the impact of the ice core site. So do you mean do we environmentally affect the site in a negative way? Is that the question, Rose?
Yes, I was wondering. Yeah,
great question. So all of these cores are generally taken from extremely sensitive and generally very well protected areas. So Antarctica has international treaties that mean that you spill a small drop of oil from like refilling your gasoline can or something, and it's a big deal. So your question is a really important one. We're environmental and climate scientists, so the last thing we want to do is actually to negatively affect the site. We have to use this fluid. We have to fill the hole up with fluid that actually keeps the hole from collapsing in under its own weight, because it takes sometimes years to drill these really deep ice cores. And so that fluid is a chemical. It's a mixture of different chemicals, and that is probably the biggest impact that we have on the site is this chemical fluid. But what we do is we make sure that we remove as much of that fluid as we can when we leave. We make sure that it is not in the part of the glacier where it can move around, okay? So it's only in the part of the glacier where it's gonna stay there for presumably forever. And in terms of carbon impacts and stuff like that, we keep trying to do our work with more and more renewable energy, so the drills themselves can be run by solar or wind power, for example. We're trying to make the drills lighter and lighter so that it takes less airplane flights to get them there, and all that stuff. So we are always thinking about making sure that we reduce the impact at the actual site and like our carbon impacts in general. What was your other question, Rose? And then I'll get to your question.
The results from Arctic and Antarctica.
Yeah. So actually, Bess is going to talk about these rapid climate change events. And what's really interesting is that they look very different in Antarctica from Greenland. And so these are, I was talking about these big cycles here of the ice ages, but what she's going to look at is these little wiggles within each cycle. And the wiggles look quite different in Greenland and Antarctica. And that's because of the way that the climate signal is transferred through the oceans and transferred through the atmosphere. And so it actually teaches us a lot about how the climate operates by looking at the differences between them. But in general, like we can see the same ice age cycle in both of them. We can see, the greenhouse gases matching in both of them. In general, the story that we get from both poles is a consistent story. And when it's not consistent, I guess what I'm saying is we can learn a lot about how things work. And then your question, Paramita, was about where does that chalk come from? So
Yeah.
most of it comes from these deserts in China. What's really interesting is that the desert dust from the Gobi and the Taklamakan deserts in China makes it all the way over to Greenland. It takes like 10 days, 14 days for the dust to make it that far. But it can do that. And actually, we can see that right now, right? We can see how far that Saharan dust is making it all the way across the Atlantic to hit Southeast United States and the Caribbean.
Yes.
So it's the same thing happening in Greenland, except the dust is coming from Asia. And if you go back in time, during the ice ages, the sea level was about 400 feet lower. And so the calcium carbonate dust, the chalk dust in particular, we think comes not just from the deserts, but from these exposed continental shelves. So the shallow parts of the ocean along the coastline has a lot of that chalk sediment in it. And we think that may have helped to bring a lot of chalk to Greenland. And again, it's actually not a lot, but you don't need much to contaminate the CO2 signal. Versus in Antarctica, it's just more isolated from the deserts in the southern hemisphere. And so there's just a lot less dust in Antarctic ice than there is in Greenland ice.
Thank you.
Other questions?
Yes, you said that the layers only go back a certain amount of time. I can't remember, 100,000 years maybe. I mean, in terms of the visible annual layers. So after that, do you rely on the isotopic records for time scale? Or?
Great question. So, each ice core has a different length of time that we can actually count these annual layers. I think the furthest back that anybody's actually individually counted layers was in one of the Greenland cores, and they counted back 45,000 years. And somebody actually had to do that, count 45,000 in annual layers. Most ice cores, in my lab, we just analyzed an ice core from the South Pole. And in that one, we counted annual layers back 11,000 years. So beyond that, how do we know how old the ice is? Well, lots of different ways. We can match up with volcanic eruptions that we know when they were. We can use glacier models that once you constrain the top 11,000 years or so, it's actually pretty easy to figure out what's below that, because the way that the glacier works, like that first 11,000 years will be most of the thickness of the glacier, and then the bottom will have time kind of squished. And so the glacier models actually do a pretty good job, and then we use like volcanic eruptions, or sometimes we can use the records themselves to try and correlate to other things that we know the time scale for. And so it's kind of an iterative process, but in general, ice cores, the reason I got into ice core science is because I used to do research on the oceans using ocean cores. Actually, from New Zealand is that map behind me. It's where I did my research for my master's degree. And I kept looking at these marine cores and wanting to understand what each little wiggle meant. But the marine cores don't have the ability to do that because there's so much uncertainty in their timescales. The ice cores have the ability to do that. And the big difference is that in the marine mud, there's ocean critters like burrowing around that mix up the sediment and mix up the time scale, kind of blur it out. We don't have that problem in the ice cores. So we're able to get much higher resolution on the time scale than we are in pretty much any other record that's out there.
Okay.
Eric?
Yeah.
I'm ready here. It's a great talk. I have a question. Although you mentioned that modern CO2 rise from humans, we know all that, but there are, starting from 800,000, we have a beautiful cyclic patterns up to today. Is it anyway what natural way of explanation?
Yeah, so what's causing those natural changes is small changes in Earth's orbit around the sun, which we
Oh.
call the Milankovitch cycles. Okay, and so this is, you can break our orbit down into 3 different parts. How circular our orbit is, and that's called the eccentricity, the circularness of our orbit.
Got it.
You can look at our axis, right? And then you can look at how that axis wobbles in space. And so these 3, when you combine them, determine the amount of solar energy that reaches the Earth at any place at any time. And so these ice age cycles, let me make sure.
So this is the Milankovitch cycle, right?
These are the Milankovitch cycles.
Yeah,
So this
that's
is the Milankovitch cycles that are driving this ice age pattern until now, right? It's the ice age, and Milankovitch has been driving the bus until now. And now we have hijacked the CO2, and we're going way beyond the natural range that we saw during Milankovitch. And I think one really important point that that I want to just make here is that what the ice core record shows us is that CO2 is a positive feedback, right? So CO2 didn't cause the initial warming or cooling that took us out of each ice age cycle or put us into the next one, okay? That was caused by Milankovitch. But what the ice core record shows us is that once you start warming from Milankovitch, CO2 goes up and reinforces that warming and makes it warmer. So it's a positive feedback. If you contrast that with what's happening now, we are artificially raising CO2 with fossil fuels. But what the ice core record shows us is that the Earth system will naturally start putting more CO2 into the atmosphere as it gets warmer. And so the natural process is going to be for a positive feedback. So even if we start slowing down our CO2, there are going to be some natural feedbacks that we have to fight as well. So it's this interesting thing. You see climate skeptics all the time say, hey, the ice core record shows us that CO2 doesn't matter because temperature goes up before CO2 goes up. But they're totally ignoring Milankovitch. We understand why temperature went up first coming out of the last ice age, and that's because of Milankovitch. But now it's totally different. We're driving the bus with CO2.
Thank you very much.
Yeah.
I was also wondering, why is it that they're measuring, or you guys measure magnesium rather than iron?
So we measure all of them. We pretty much everything on the periodic table now gets measured in an ice core. Magnesium, so there's a group of 6 elements that represent about 99% of the stuff that's in an ice core. And so that's magnesium, calcium, sodium, potassium, and then some anions that go with them. And so the reason that we measure magnesium is because it's easy to measure because it's at a much higher concentration than, say, iron. So I actually have a different instrument that I use to measure the magnesium, the calcium, the potassium, the sodium, and the nitrogen and sulfur. Those are those 6 key elements. I have one instrument that measures those. And then I have a much more sensitive instrument that measures pretty much everything else on the periodic table, including aluminum, including iron. And what you see is that for the most part, if your magnesium is coming from dust, then your aluminum and iron will all look the same. They'll all look like that magnesium. But these days, we pretty much measure it all.
Okay, I was just thinking about the iron, that goes into the ocean from.
Yeah, iron fertilization, right. Other questions?
You had a prediction, or not prediction, but a CO2 from that has gotten this high. Like, I can't remember what you said, how many millions of years ago it was. How did that number come about, or at least, you said it's not sure.
Right. So
yeah.
How do we know beyond the ice core record?
Yeah.
Great question. So there are lots of different proxies that attempt to understand CO2 back in time. One of them is you can look at fossils of leaves, and the leaves have little holes in them that they use to exchange gases, right, to bring in the CO2 for photosynthesis. And the hole, the diameter of that hole is proportional to the CO2 in the atmosphere. So they can look at that as one thing. There are different chemical proxies that you can use to figure out what the pH of the ocean was. And the pH of the ocean will be dependent on the CO2. Like we know now, as CO2 goes up, the ocean's getting more and more acidic, right? And so there are ways of trying to tease out CO2 from past changes in ocean acidity, which gets recorded in ocean cores. The problem with all of these is that they have huge uncertainties. So when I say huge uncertainties, I mean, once you get before the ice core record, the uncertainty bounds can be several hundred ppm, right? And if we say the natural range that we've seen recently is just a couple hundred ppm, then you're talking about the full natural range of uncertainty going back in time. We do know that if you go back 60 million years ago, it was a time when the Earth was much warmer. We're talking, 25 degrees on average warmer, no ice anywhere on the planet. You got palm trees up in the Arctic. You've got warm loving animals up in the Arctic. And we can see that CO2 was probably over 1,000 back then, naturally. But then it took about 60 million years for that CO2 to come down to where we are today until it started, bouncing back and forth during ice ages.
Is that CO2 associated with the asteroid impact and the burning of vegetation?
No, it's not in this case. What we think is that CO2 comes out of these larger carbon cycles that have to do with plate tectonics. So volcanoes emitting lots of CO2 because the oceans were spreading faster back then as Pangea opened up, right? As the Atlantic Ocean formed, a lot of CO2 going off. But the thing is that we're talking about orders of magnitude different scales, right? We're talking about millions of years time scales. Instead of now, we're talking about years and decades, right? So it's really hard. It's difficult to talk about these things to students and have them understand the massive amounts of differences in time we're talking about. Because 50 million versus 50,000, do they really have a sense of that difference? Sure, they know the million's bigger than the 1,000, but like 50 million years ago, we're talking not far, after the dinosaurs. 50,000 years ago, we're talking, life basically like today, except that we're hunter-gatherers instead of, the societies that we are today. So it's hard to get across those differences in timescales when you talk about it with students. So it's something that I think you got to build up this concept of deep time, which is probably what earth science is one of our, it's one of the most valuable things that earth science teaches us, is this concept of deep time.
Was that 16 million years ago carbon dioxide related to any of Milankovitch cycle, like any one of them?
Nope. So totally, again, like Milankovitch cycles are on the order at longest 100,000 years, but here we're talking 16 million years. So it has nothing to do with Milankovitch. Milankovitch would have still happened. Milankovitch is a fundamental part of Earth's orbit around the sun. And so if you were actually measuring the temperature at that time, you'd probably see Milankovitch cycles, but there's no ice. And so those Milankovitch cycles don't really get amplified very much. And those Milankovitch cycles would be at a much, much warmer, average time or average level than the Milankovitch cycles we have today, when CO2 in general is lower because of these larger plate tectonic forces.
I have another quick question is, how do you control, or do you have to control for compaction if you're looking at the top part of the core and trying to judge the depth of the snow?
Yes, absolutely. So each layer, you can imagine, when snow falls on a glacier, it's light and fluffy. And then as each year of snow falls on top of it, that year gets squished under the weight of the overlying snow. And so these layers get squished and squished, where they go from snow eventually to ice, but then even once they turn into ice, they keep getting squished, and now you're actually squishing the ice and making a layer that might have been this thick of ice, you're squishing it even thinner. And so yes, we absolutely have to correct for that in pretty much all of these measurements that I'm talking about. We need to correct for this squishing of the layers on top of the thicker ice above.
Erich, will you discuss the melting in terms of nowadays and these massive melt events that we're having, and how that compares to the melting you referred to earlier?
Yeah, so I think, you know, I'm doing a lot of research right now on about a time about 8,000 years ago. I mentioned in, where did you go? Here. That this is the most melting that we've seen in at least 450 years, because that's how far this ice core record went, but probably 8,000 years. And so you might ask, like, well, what happened 8,000 years ago? Well, 8,000 years ago was a time when Earth's orbit was such that the summers were warmer than today. Maybe, you know, 5-6 degrees warmer than today's summers, at least up in Greenland. And that's actually what pulled us out of the last ice age. It was that part of the, we were in a warm part of the Milankovitch cycle, and that actually forced us out of the last ice age by making our summers particularly warm. And then over the last 8,000 years, the summers got colder and colder and colder as Earth's Milankovitch, you know, the Milankovitch orbit slowly changed. And so we, this, you know, it's, so again, it's kind of hard to talk about, right? Because it's not really apples to apples. So we know that if, here's one key thing. We know that based on Milankovitch, we should be getting colder and colder and colder and colder through time, right? And yet, despite that, we are seeing record high temperatures. And so what we're trying to figure out now is how much did Greenland melt 8,000 years ago, right? Because that's another window into our future. And it looks like Greenland melted quite a bit 8,000 years ago. I think one take-home message that we get from the ice core is that it's really hard to grow an ice sheet and to grow a glacier. It's really easy to melt them back. And the way you can see that, I'll pull this figure up one more time, is this sort of sawtooth shape of the temperature. So it takes a while to build up the ice sheet, but then the warming cycles, see this is a warming, this is our last warming, are really quick. So it took us somewhere around 80,000 years to build up Greenland and Antarctica to the skies that they were during the last ice age, which includes here in Hanover, New Hampshire, we had a mile of ice on top of us, right? And then in the span of just 6,000 years, we melted that entire ice sheet, the ice sheet that went all the way down to Long Island in New York. It covered all of Canada, all the way down to Long Island. We melted that entire ice sheet back in just this 6,000 years, after taking somewhere around 80,000 years to grow it.
So I think Russ and Matt, when we were doing this activity, you both asked about why we didn't pick nice even years to put those data points on there. And those data points were chosen so we could pick the interglacial and the glacial periods. The kids could actually calculate how many years then it takes to go into a glacial and how many years it takes to come out of it. So it's different than that.
Yeah, I mean, one statistic about this difference between the natural and the human-caused CO2 change, during this 6,000 years that we melted the ice sheet back, it took, that was a CO2 rise of 70 parts per million. And then in my lifetime, I'm 43 years old. In my lifetime, we've seen exactly that same amount of CO2 rise. So what took 6,000 years naturally and melted an entire ice sheet that covered all of Canada, all the way down to Long Island, is the same amount of CO2 change that we've seen in my lifetime. It's mind-boggling.
So
Other questions? We're probably getting out of time here, right,
yeah,
Louise?
I think we're starting to run out of time, but we're thrilled that you're going to come back with us a little bit later on and do the virtual field trip, and they can ask some more questions at that point. Maybe this can sit a little bit, and Bess is coming in later too, so they'll be able to get some more information and have some more questions for you this evening.
Perfect. Sounds great.
This evening, your time.